Hey everyone, welcome to Ceph Tech Talk. It's been quite some time since we've had a Tech Talk, so thank you all for offering to give us some content. If anyone is interested in giving a Tech Talk, please reach out to me. I'm Mike at ceph.foundation, and you can probably find my emails on the Ceph mailing list as well. But let me go ahead and introduce Yuval. He's going to be speaking on Lua scripting and the RGW. And this will be a code walkthrough. So Yuval, will you please begin?
Hi, thanks, Mike. So yeah, that's what I'm going to do. I'm going to do a code walkthrough. I'm not going to give too much background or demo the Lua scripting on the RGW. I have a couple of presentations about that. I had a talk in Open Source Summit in Austin last summer, where there's a full explanation and demoing of the Lua scripting and there are other resources as well. But this is really focusing on the code walkthrough, and the reason is that the way I envision the Lua scripting feature is that it should grow. So I'll explain in a second, but it can grow in 2 dimensions. One is add more places where we put Lua hooks. So currently there's only a few places, but if people think there are other places that could benefit from more Lua hooks, and I want to show how the Lua hooks are done so people can do that in other places as well. And the second thing is, even if a Lua hook exists, maybe people want to expose more data or to allow more actions on the data that is exposed. So I'm going to show how you add more fields, make the fields writable, for example, all kinds of things like that. That again, this is a work in progress. So the more people know how to do that, to be more effective. Let's start. The first thing I'm going to show, like the presentation just have like 2 slides, so it's mostly looking at the code, but I want to give like a very quick map of the different files. So you would know which files has to do with Lua and which files kind of do what functions with Lua. So I guess the most important files are the files that are actually implementing the data access to in the different contexts. So as I said, Lua, it's a scripting language, but it has to run in a specific context. It can't just run and touch whatever it wants. And you have to expose from your C++ code the values and the data fields to this specific context. So the most important files are the RGW Lua request, and this is what exposed the S3 request context. We have 2 contexts. We have pre-request and post-request. We have the RGW Lua data filter, and this is also kind of in the request context, but it's slightly different. It is for put and get operations, you get access to the actual payload, while in the request, you don't have access to the payload. You have access to all the fields of the request itself. There is a Lua background context. This is something between a POC. It's not completely mature. I'll explain that in a second. So those are the important files that actually do the heavy lifting of the implementation of Lua. And there are also files that kind of support the whole operation. So in RGW admin, this is the Redis Gateway command line interface. This is where you put the scripts, and you can also do package management if you want to have Lua package dependencies that use in your script. For example, you want to use JSON in your Lua code, then you need to get the JSON package. RGW Lua is what actually implements this script and package management. And because both the package names and the actual content of the script, like the actual text of the scripts, they're stored in Redis object. So we have the RGW cell Redis file where we actually implement putting those scripts into Redis objects. RGW cell, this is the high-level interface because now we have the zipper architecture where you can store things not necessarily in Redis, but only Redis implements the Lua bits. So this is for the script management. And last but not least, we have the RGW process and RGW op. So RGW process is where the pre and post request context scripts are being invoked. This is what really calls the hooks. And RGW op is what calls the data hooks for the put and get data scripts. The background context is being invoked from, well, I mean, it has its own thread, so it invokes itself. But the whole thing is being set up, this special thread is being set up in RGW app main. This is another thing that is important in app main. This is what installs the Lua packages that you configured via the admin CLI. And that's pretty much it. So this is really a high level kind of mapping of the different files that that are touching Lua. We do plan of adding more functionality with the script management, so you can have more than one script per context, for example, things like that. But this is really the core development of Lua. Of course, you're welcome to assist them as well. But what I usually see is as contributions from the community is, as I said, adding more hooks, adding more fields. So that would probably go either in the Lua request file or in a new file if you want to add a new place for Lua hooks. So the code walkthrough is going to go through hopefully all of these areas. I'll start with the script and package management. Then I'll explain a little bit about the package loading. Then we'll go through the request context, the data context, and the background context. So that's pretty much what I have for the presentation. Okay, so let's start with the script management. So please let me know if you want me to increase the font, but if this is okay, then I'll stick to this. So we have a couple of new commands in Redis Gateway admin CLI. There's a script put. This is what really uploads the script. And what it does, you give it a file. So the file is just a Lua file that you want to upload. It reads the file. It does something called verify. This is very basic verification. So what verify does, it makes sure that you don't have any syntax errors, but it doesn't mean that there are no errors in the script. And the main reason, and I'll show that later, is because all the parsing of the actual Lua is lazy. So it means that if you have a really ugly syntax error, then the verify function would catch that. But if you're kind of accessing a field that doesn't exist, or trying to write to a field that is a read-only field or something like that, then the verify function cannot catch that, because we're not actually building the entire structure of fields, because we have no idea if we're actually going to use them or not. So again, it's lazy parsing. So if you have some garbage field name, but it's under some if-else condition that doesn't happen, then the Lua script would work fine. There'd be no failure. So this is why the verify cannot actually verify the full correctness of the script. But if you have some basic syntax error, it would verify that and return an error, say something is wrong. So this is the verify function. So if everything is fine and you provided the correct context, so you have to give a right context to the whole thing, then we have something here called the Lua Manager. This is the SAL interface that kind of abstracts the writing to the Redis object. And so you get the manager, and then you call the write script, and we can see here, and this is the RGW file, that the only thing that the write script does is that it's accessing this SAL Lua Manager that is supposed to have something called a put script. The only SAL Lua Manager that implements the put script is the Redis one. So you put that in a Redis object, and this is fairly simple. So it just uses a system object where it stores the actual Lua code or Lua script. It's just a text file that is stored in a Redis object. So this is very simple and straightforward. This is the putting a new script. You have another command for getting a script, and the last command is to delete a script. So there's nothing special here. I won't explain too much. It's just storing the whole thing in those Redis objects. The commands that are kind of maybe more interesting are the commands for the package management. So as I said, in your Lua scripts, we allow for using external packages, and this is very useful. Like if you want to send something from Lua, you need a socket package. If you want to do some JSON parsing, you need a JSON package or any package that you want. There are different examples for how people are using packages. And the way the packages are working is that, well, a Lua package, we use a Lua package manager called Lua Rocks, and a Lua package is a whole bunch of things. So a Lua package is usually a couple of Lua files together with some C files and a make file, something like that. So usually if you look at most Lua packages, when Lua Rocks tries to install them, it compiles C code and copies over some Lua files, which are just text files. And because of that, we can't really store a Lua package inside Ceph somehow, like we did with the Lua script that are just text files, because it's compiled code and we have no idea like where you're going to run that. So the only thing that we do when you add package or remove a package is we add or remove the package name. So when you call the admin CLI command and tell it to add package, we do write something into a Redis object, but you're just writing the name of the package that you want to add. And the same goes for the remove. So we're actually not adding or removing anything. We're just writing the name of the packages to a file. So that's about the management. You would also see that everything that has to do with Lua packages is protected by an if-def, and this could be macroed out in CMake. The reason is that packages, they could be risky. So you may decide that if you have your own version of Redis Gateway or Ceph, and you want to support Lua, but you don't want people to add packages that would kind of allows the Lua code to get out of the sandbox and do all kind of risky things, then you may want to disable that completely. So this is why we have those if-defs. And other than that, I mean, all the commands of the remove package, this package, and so on, they follow kind of the same concept. And you would see here like the add package and the remove package in the cell Redis file. It's just updating the well, we're using the OMAP keys for the packages. We're not really storing that inside an object, so it's easier to just search for them and remove and add them, as those are just kind of attributes. So these are the functions that actually implement that in Redis. So this is about the script management and the package management. Next thing I'm going to have a look at is, okay, so how do we actually do the packages themselves? So in RGW app main, you would see the code that does that. And what it does is, again, protected under this kind of if-def, there is a command to do install packages. So install packages happens only on the startup of the Redis gateway, which I agree, it's pretty ugly. It means that if you want to add or remove package, it would only take effect the next time you restart the RGW. And the reason for that is that the installation of the package is something pretty heavy. I mean, in the future, we probably would fix that and allow for a specific command to go and do this installation. But overall, we cannot just install a package when somebody puts a new package, because this actually requires, it invokes a Lua rocks command that can cause compilation and all kind of things to happen. So that has to be done with care. Currently only on startup, but it probably would be fixed in the future. So you don't need to restart the RGW for that to take effect. There's also something here that has to do with isolation of those packages. So usually Lua rocks, when you use it, maybe we'll go to this file. So you see the actual implementation. So usually when you install something using Lua rocks, it would install in some canonical place, like, I don't know, /opt or /use or something. But we want this installation to be isolated just for this specific RGW. So, for example, we have multiple RGWs running on the same host, or if you have Lua running on the host for whatever things that you want, we don't want to mess with that. We don't want
Yuval, you're cutting out right now.
Sorry. Sorry. So maybe I'll just repeat.
Yes.
Installation of the packages is done in a specific place for this specific RGW, because we don't want to interfere with any packages of Lua that were installed on the machine. We want to allow for multiple RGWs that are running on the same machine to install packages and not interfere. So we have a specific directory for each running. And we're looking for Lua rocks, and then here is the kind of the magic happening. So for each package, we are invoking the Lua rocks file, and we're installing. We can have a specific version of the pack, and the -3 command is telling what is a specific path where this is being installed. And then later on, we also want to see if there are issues or so on. So we kind of reading the standard error and standard out from the Lua rocks command, and kind of taking the information and putting that back into our logs. So if for some reason the installation failed, then people would have the information of how to debug that. So I think this covers all the bits that are needed for the management. So we know how the code works for managing scripts. We know how the code works for managing packages, and what actually is happening when we add or remove a package. Now, what we do here, because of the adding and the removal, so everything is kind of easier. Whenever we're calling this code on the RGW startup, we remove all packages that were ever installed in this specific directory, and we're reinstalling all the new packages, all the packages that we have configured. This is how, like, the removal and everything works easy. If we would like to do that in a more dynamic and efficient way, we'll have to think of how to do that. But when it's happening on startup, this is probably okay. I don't know, maybe I'll take questions now before I move to the actual implementation. This is more about the management of the Lua scripts. Okay, maybe if you have questions, we can do that at the end as well. Okay, so now we're getting to the more interesting thing. So this is the pre and post request context, and this is the context most people that are using the Lua scripting on the RGW are using. So how do we do that? In RGW process is actually what's kind of hooks or ties together the front end, the beast front end, with the actual implementation of different S3 operations. And this is where we are doing this. So before we actually do the operation, we have the pre-request context. And this is before the operation is being executed. And this is why you don't have access to some things here. So you have access to everything that came into the RGW, but you don't have access to things that you're fetching from the actual object or bucket or anything that is actually stored in Redis. So this is why people sometimes they write code in the pre-request context, but they don't have access to all kinds of things. And this is why it is happening, because this is before we executed the request or the operation. And the whole process here is really pretty straightforward. We read the script for this pre-request context. If there's no script, there's nothing to do. Like this is the common case where there's no script. If there is script, we're calling the execute command. And this is in the pre-request, and in the post-request, it's pretty much the same. So this is after the operation is done. So everything is done, everything is complete. This is before we reply whatever we built with the reply. So you still have a chance here to change things with the reply. So if, for example, you want to change the error code of the reply or change something, some attributes in the reply or whatever, then you can still do that because the script runs before we actually do the reply, but after the operation is done. So there's no point in kind of saying, oh, this put request failed and I didn't put anything, because the put request already finished here. So you cannot undo whatever the operation was already doing, but you can change the actual values that you're applying. So, and again, the process here is simple. You read the script. If the script exists, you call execute. So let's see what execute does. Okay, so this is the execute function, and we'll go through that in a little bit of details. So the first thing the execute function does, it creates a new Lua state. This is what creates the Lua VM. So this is important to understand. We instantiate the Lua VM for each request. So this is why there be no locking or race conditions or anything between the different Lua VMs, because we have a separate VM for each request. It does have some overhead, but the whole point about Lua, or the beauty of Lua, is that the VM is small in size and very, very fast to be created. I don't have the exact numbers, but it is pretty fast. The next thing after creating the VM is we want to allow the standard library. So what we do here, and I think this is the Lua utils. Oops, sorry. Is that we're opening all the standard Lua libraries, but we're disabling some of them. So because some of the libraries, it just makes no sense in the context of running a Lua script on the request. For example, part of the standard library is loading Lua scripts. I don't think we want to load the Lua script inside the Lua script. The debug commands that, again, they don't make sense here because you have to tie them to a C function. We don't want people to be able to exit, because this would just call exit and crash the Redis gateway. And in the future, we may have like some configuration flags that allows the standard library to be even more restricted. For example, the entire OS library, we just disable exit, but you can do, currently, you can invoke bash script from Lua. Now, whether it makes sense or not, this is really debatable. But the good thing about this function is that you can control that. And we may decide later on to kind of make it even more sandboxed than it is today and not allow for other things. Of course, there are standard libraries that always needed, like math libraries, string manipulation libraries, stuff like that. Of course, everybody would need that. But this would not break the sandboxing of the Lua VM. So currently, we allow some breakage with what they call the OS library, but we may restrict that furthermore in the future. Okay, so we did that. We set the package path. If you're using some packages, this is the path that where we installed the packages when the Redis gateway started. And we create some action. So actually the only action that we allow currently in Lua is to write something to the debug log. So this is the create debug action. And we also allow invoking the ops log action. So this is our own action, and this is just tying to an existing stuff. And there's something about the background. I'll touch that in a minute. The most important function here is the create meta table function. And I'll explain the overall concept that I have here with the way it's structured, because this is, again, where you probably would like to add your access to fields and so on. So I'll touch that in a second. And then we actually, the doString is what actually runs the Lua script, and we have some error handling. So that's the execute function here. So what does the create meta table does? So let's have a look here. Okay, so the idea that we have here is that, like in Lua, you have tables and you have meta tables. So table is usually where you store your data, and meta tables, those are like allowing for polymorphic behavior on the tables. So what happens when you access the table, write stuff to them, read stuff from them, iterate them, count the size, and so on. The thing is that we don't want to copy data around. And the data exists in our C++ structures. Like we have in the RGW, we have C++ structure holding all the information that you need. So we don't want to copy them over to some Lua table. So our tables are actually empty. There's nothing. There's absolutely nothing in our implementation that's holding data in any Lua table. The only thing that we have are meta tables. Why we need that? Because we're using the polymorphic behavior of the meta tables in order to kind of allow the Lua code to access the data that we store in the C++ structures. So when this create meta table function is being invoked, it does create a table just because you need a table for every meta table, but it doesn't use the table for anything. And the way that, because I did not want to use like some inheritance hierarchy and so on, so you're actually creating a meta table that is implementing the actual access to the different fields. And what you do here, you just have the create meta table function templatized with a table. So there's no inheritance, and you can actually, as long as you implement the correct functions, then you're good. And I'll show how it works. So let's say that you want to give access to some field in the request, so you have to create a meta table for this field, and then at the right place you create the meta table. You invoke this function and you pass it the value of the class that implements different ways you access them. The up values is like the different functions in this meta table class are actually closures. So you have to kind of it's like you have the capture variables in the C+ lambda. You have what they call up values here. So you capture the actual references to the C object, and then when people are invoking the different functions, they have the specific pointers already kind of in their hands. So this is why they can use them. So I'll show that in a second. So what does it do? It takes all those app values. Those are usually pointers to C++ structures. It creates a new table. If it is a top-level table, it gives it a name. Other than that, the tables don't have any names because they're just like the structure is like you have something dot something dot something, and all those fields that are kind of concatenated via dots are the different tables, but they don't have their own top-level names. Only request is the only top-level name that we have. So this is why we give it a name. But other than that, we don't give it a name even. So we create a new meta table, and then we start to implement the different callbacks or different kind of polymorphic hooks of the meta table. So the first thing is index. Index is when you have something dot or brackets in Lua, and because the table itself is empty, so if you access the table via a dot or via brackets, it would not find anything. So it will go to the meta table and see what it needs to do there. And what we do here is that, first of all, we pass in all this captured values, the up values, and then we pass it the actual closure, and we know that the closure has to be called index closure. So in whatever class that you created here, and you passed to this templatized function, this class has to have a function called index closure. And this function will get all those app values and would be invoked when somebody is accessing the table with brackets or with dot, and pass it the index that it passed after inside the brackets or after the dot, and would also have the app values stored somewhere. So you have the index, you have a new index. New index is same as index, only for writable values, like if you want to write something into the table. Pairs is the way you iterate over the tables, and len is when you do the Lua hash sign, which gives you the length of a table. So you need to implement all those closures, or not. I mean, you don't have to. Like if something doesn't have a length, then you don't implement it, or you implement it and give it an error or something. And then if somebody invoke a length on a field that doesn't have a meaning for length, then it will just give an error to Lua. And the last thing that this meta table, this create meta table does is tie the table with the meta table. And this is what it does. So I understand this is pretty abstract. So we'll go to see an actual example of that, and that would probably make it simpler to understand. So the first meta table that we create is the request meta table. Now this is a top level one, so it actually, the table has a name, but other than that, the fact that it has a name, it's fairly similar to the other ones. So let's look at the implementation. So I said that I don't do any inheritance. I do inherit from an empty meta table. The only reason is that if you're lazy to implement some of the functions, that doesn't do anything. So if we look at what this one is doing, the only reason we have this is that it implements all the functions that I assume that exist, like the new, well, almost all of them, the new index closure, the pairs closure, and the length closure, and it gives an error if you invoke them. Otherwise, I'll have to implement that in many places. The reason I don't implement here the new closure, the index closure, is because you need that in each and every table or thing that you, otherwise, why do you even create that? So if you forgot to implement the writable one or the iteratable one or the length one, then I assume that you didn't want that, and I'll just give an error if somebody writes Lua code that access it. But if you forgot to implement the index closure, then you have a bug in your code. You need to implement that, otherwise it's meaningless. So the top level one called request, the top level one called request, and you can see the name here, and you cannot iterate it, you cannot change values to it, and so on. So this is why the only closure that is implemented here is the index closure. And here you can see a long list of things that, or fields or subfields. So it means that whenever you write in Lua request dot something, it has to be one of those fields. So if you write request dot RGW op, then push string just pushes the op name as a string, and then you can do whatever you want that in Lua. If you wrote request dot decoded URI, then I have this up value, right? This is like what is captured in the closure. So I have this up value, which is the request state, and this is kind of a huge C structure that is holding pretty much everything about the request. So one of the things here is decoded URI, and you can go on and see that whenever I'm exposing something which is just a string or an integer, it's pretty straightforward. Sometimes what I'm exposing is something that is itself a table. So is itself has dots and can have more level of hierarchy. So whenever I'm exposing this, I cannot just do the Lua push, which just puts a value somewhere in Lua. I need to create a new meta table. So what I actually push here, I push a new meta table, so or a new table with a meta table that if somebody is, for example, writing request.generic attributes dot something, it would know how to do that. Generic attributes, it's kind of a map, so it's slightly more complex, but I can take a simpler example. So let's say that you write request.bucket. So what's going to happen here, I'm going to create a table that has nothing in it, and this table is going to have a meta table that knows how to access the different things that has to do with a bucket. So we can have a look here. And again, it inherits from this empty meta table just to implement the things that are not implemented. And it's pretty much the same thing. You see, well, the bucket also have this up value. The up value here is, again, the request state. And kind of one of the reasons it is the request state and not the bucket as the app value, because sometimes I don't have the bucket, but I still want to have the bucket name. And this is why I'm using, like, for example, here, like, especially like in pre-request context, you don't have access to the bucket object at that point, but you still know what the bucket name, because it's coming in the request. So I'm checking whether if the bucket is empty, I'm taking the name from here. And you can get the tenant, the name, like you can get all kind of things from the bucket here. And some of the things by themselves are also another level of a meta table. For example, if you have something like request.bucket.user, then it goes another level because user itself holds more fields in it. So you can see here that the user has a tenant and an ID, and this can go on to whatever levels of hierarchies that you want. So if I won't go through, of course, through all the fields and all the things in this place, but you can see that the way that you would like to expose new fields is, know how to access them from the C code, pass the C structures as pointers, as up values to the functions, and create a new meta table kind of class, and plug it in the right place that you want, that it makes sense to access. I'm going to show two more things here. One would be around tables that are or fields that are writable, and the other one would be around things that are iteratable. Whatever that. Okay, 1 second. Okay, so let's see, new index closure. What's this one? Okay, so the bucket meta table actually does allow writing, but as you can see, the bucket has lots and lots of fields in it, as we've seen before, but only one of them you can actually override. So the thing that you can override is the name. So for the whole thing to be writable, then I need to implement the new index closure. So if somebody is doing request.bucket.name equals something, then it would jump here, like this is the meta table mechanism, the polymorphic behavior Lua is allowing, and would jump to this function. And again, it would take the app value or the value that captured in the closure. And if somebody is calling bucket.name, then I'm allowing this to be overwritten. If I'm writing something like request.bucket.mtime and trying to override that, then it would fail, because I will compare the index and it's not name, then it's either an unknown field or you're trying to write into something that is not writable. So this is an example for implementation of writing values or override. Like here, I'm actually overriding the actual value. And this is useful, like, for example, if you want to steer messages to different places, to different buckets than the original message or something like that, and then you can do it here. Pairs closure. This is a little more tricky. So the way that you do iteration on a table in Lua, you write like a for command, and you have like a special keyword called pairs, and you put inside the parentheses the name of the table that you want to iterate over. And what is resulting from the pairs are key value pairs, and that you should get like inside your for loop, you can get a key value that iterates over the entire structure. So we have all kind of places where we have like in our C++ code, we have something that is iteratable, like we have maps and other things. So this is a grant map. So again, in order to get that, you have to go pretty deep. There's the ACL. So this is part of the request. So you have a request dot, let's say, user ACL, and this creates a table of ACL. And in this ACL itself is not iteratable, but if you do ACL.grants, then the grants, you can iterate over them because I have the pairs closure. And the way that currently it's done, it's called a stateless iterator, the way it is done. So every time you do an iteration, you pass the new key and value to the next call of the iteration. And then I'm searching for them, I'm getting the values, returning them. Sorry. And sorry, and the next iteration is taking the key, and you find the last key, you move ahead one value to the next iterator, and then you pass the next key to the next iteration until you reach the end, and then you return like nil, and then Lua knows that the for loop needs to end because you got the nil key. So this is the mechanism. It's a fairly robust mechanism because you just keep on looking up new keys. It doesn't work well with multi-maps, so this needs to be fixed in the multi-maps, and it's highly inefficient because you do a find every time. So you get like the next key and you increment the next iterator, but you forgot about the iterator, and you just return the next key and look up the next key. So it's a very inefficient way to iterate a table. So I'll be fixing that. I'll need to somehow create the iterator as an app value so I can pass it to the next invocation. Because the only thing that Lua is passing to me is a string key. It cannot pass me an actual iterator. So I need to store the iterator as an app value and manage it somehow. So, but that I'll fix that hopefully soon. But currently, this is how, if you want to iterate something over a table, so you have a structure which is actually let's say, an STD map or something like that, then this is the way to implement that. You have to just copy that from the examples that we have here. So that's about the request context. I know it was, lots of things to consume, but hopefully next time you look at the code, you get a better understanding. And of course, if you have more questions, please shoot me. What I've seen is that in the past, people added stuff or made something writable, and the change itself is pretty straightforward and simple. So it shouldn't be too bad to add things. Okay. The next thing I'm going to show, and hopefully do that much more briefly, is the data context. So the data context is invoked from the RGW op. So I allow to traverse data only in put object and get object. So both put object and get object, the way that Lua works is as a filter. Now, not to be confused with the zipper filters or something. So the put object and get object, they have a filtering mechanism where currently it's used for compression and encryption. So currently I'm also adding the Lua stuff there, and you can see where this is invoked. So in the case of the put object, I'm invoking the Lua script before data is compressed and encrypted. So I'm putting that as the last filter, because the way it works, it's the last filter runs first. So I'm putting that last. And in the case of the get object, I do the opposite. I'm putting the Lua filter first because I want it to run last, because I want that to work on the decompressed and decrypted data. So that's where I put that in the RGW op. And what it does, when it comes to what kind of fields and so on it exposes, it is much, much simpler than what we've seen in the request. So it exposes a field or a table called data. The data is actually an iteratable table that is just the buffer list, and you can iterate it byte by byte. It also have a request called you also have access to the request, so you can access the request itself, and also the background, but we'll put that aside for now. You see the execute function is pretty similar, although much simpler than the execute function of the request context. So you have the data field, the request, and I also have the offset field. I'm not sure what it is, but it's something that is available there, so I just added it. But the important one, of course, is the data field. The data field is implemented in this class. So you can access the data using the brackets, and those are just offsets, like it's just a huge array. So data brackets, 15 is the 15th byte. You have to make sure that you pass the right indexes, because Lua starts counting from 1, and we of course start counting from 0. And you also have the iteration one, because you can actually iterate the data. So you're gonna iterate that byte by byte, and this is how we expose it. The key here is just the index, like just the running counter of what you're iterating, and the value is the byte value of what's inside there. So and of course we have the length. So this is the whole thing about iterating the data. Now it's not iterating the entire object, because it's just iterating whatever is coming inside the request. So whatever is in flight inside the memory of the RGW. So not actually iterating an entire S3 or Rails object, just whatever is coming in the request. What you can do with it, I'm not sure. I have in this open source summit, I had a demo showing how I do entropy calculation on data entering the Redis gateway and trying to implement some kind of a algorithm. It's really a demo, not something too real, to detect malware based on the level of encryption of the data that is incoming. So, for example, you can do this entropy calculation just by traversing this buffer list, this data coming into the RGW. Last but not least is the background context. So I'll do that really quickly, but the background context has two things. It has, first of all, a context by itself. It's just a thread that is periodically running a Lua script that is put in the background context. And because it's just a special thread, it doesn't have access to anything, almost. So it's kind of useless. However, unless you just want to do something periodically in, I don't know, in Lua. But there's also like a global table that we call the RGW table. And the background context does have access to this table. Now, the thing is that all contexts have access to the table. And unlike what I said about that every VM is its own kind of sandbox world with no access to any other VM, this is actually a mechanism to allow communication between different Lua scripts or different invocations of the same Lua script. So, for example, you want to count how many times you ran a Lua script in the pre-request context. There's no way to do that, because if you do that in Lua, then this information is lost when the Lua VM dies, and the Lua VM dies when the operation ends and you send the response back, unless you put that in this RGW table. So this is a global table that survives
Hey, Yuval, you cut out again.
So that's right. So the same table, they're all synchronized with this mutex, which is very inefficient. But it does give you something. The table, of course, you can read and write from it. So it has the index closure. It also have an increment and decrement atomic actions. The reason is that because it's a shared table, if you try to read, increment, write from Lua, then there's no atomicity that is guaranteed, because you can be reading one value, incrementing that in Lua. By the time you wrote the value, there was some other instance of a Lua script that already changed the value. So we added atomic operations that are done atomically inside C++ that does the increment and decrement. But other than that, you can set and get values. And as I said, it's really a POC level because of this global lock. It does have some nice features. It is using, like, when you write or read values from the table, the values could be, the values doesn't have to be, the key has to be a string, but the value could be a string or an integer or something else, and we have some nice mechanism to do that. But I won't get into that now because I think we're running out of time. So this is pretty much the end of this presentation. We have like 5 minutes for questions, if you have some questions, and if not, feel free to shoot me emails or ask me questions on Slack or anything.
Feel free to put questions in chat. I see that Tom Bennett.
Yeah,
Is there
thanks.
any
Sorry.
documentation? Oh, go ahead. Sorry.
Yeah, cool. Yeah, Yuval, thanks. Yeah, this is obviously a very interesting talk, and we are certainly, for implementation, we're going to be using Lua quite extensively. I just wanted to check. I mean, obviously, I know about the requests, the request field that you can access. I didn't know much about the data and the background context with the the Rados gateway table. Is there any documentation anywhere that kind of just or example code somewhere that uses this so I can kind of just get a feel for how to use it?
I'm just checking the documentation, like the official upstream doc. I'm just going to paste that. So I see that I have I've mentioned the background and the data context, but maybe I didn't write the proper documentation for the fields. Let me check. Yeah, so you can see there's a background context. There's it is documented, maybe not well enough, but I have something called background context section there, data context, and I have the global RGW table explaining about this table and even mentioning of the increment and decrement functions.
Yeah. Okay. Cool. I've just seen that now.
Okay. Yeah. Maybe it needs more example. Oh, I even have an example. I see. So if you scroll all the way down, I've even wrote my object entropy function that is using the data context in order to calculate the entropy of the buffer list. So you can even see that.
Cool. Thanks. Yeah, that's awesome.
Okay, great. Thanks.
Thanks, Tom.
Yeah. I had a follow-up question if there aren't any other, well, actually just a comment if there aren't any other questions.
Mm-hmm.
Sure.
Yeah, so I was actually, because you're talking about, so something that we want to do is we want to manipulate requests coming in, and when somebody does a request that we don't want them to do, we want to be able to return an error as opposed to complete the request. And obviously, I mean, from your talk, you've confirmed that you can't do that, but we've decided we want to do that. So I thought you might be interested to know that what we do is we actually just manipulate the storage class, which is a very simple way to. So we manipulate the storage class and then return an error message with some bits of information. So what we do there is we create a storage class, or in this simple example, we had said something called unavailable. And so that's not a storage class that is defined inside the Rados gateway. So we were very easily able to do things like stop deletes. If we want like a worm style Rados gateway where we write stuff, but we never ever want to delete it. So we want to absolutely be guaranteed that if anybody comes in and tries to delete stuff, that they can't. And I mean, it's amazing with a couple of lines of code how we could very easily manipulate the request coming in and say, sorry, you can't actually do this, and then guarantee that no matter what happens, you can't actually delete data. So it's already proved for our use case, and I know we are a very particular use case, a very powerful tool to manipulate the requests coming in and obviously then look at requests going out. So it's been extremely useful. Yeah, I certainly think we'll have as we move on and develop more code, we'll certainly have more interesting questions. But this has been extremely useful. It's been great to kind of look in and see kind of that when we start actually wanting to understand the stuff where we can look. So one other question is where in Ceph do you actually store the bits and pieces that make up when you execute the Lua rocks? Where in Ceph is that actually stored?
Okay, so the thing is, there's maybe I'll show that. It's probably here. Okay, yeah. So when the RGW is starting, then I'm invoking this LuaRox install, and -3 is the LuaRox path, and this is where the whole thing is being installed. So, and the path is a very specific one. It's like specific to the RGW. I don't remember exactly, but I mean, you can see it in the code what the default path is. You can change it. It's a config variable, so you can change the path to something else. Yeah, there were a couple of issues that you guys found in containerized deployments when it came to LuaRox. I hopefully fixed that. I had a couple of PRs to fix that. But yeah, I don't remember what the default path is, but maybe it's here somewhere.
Yeah. So that's the path on the file system. So I was more interested in where it's actually being. There was stuff installed in Ceph as well.
So in Ceph, I'm not storing. I'm not storing the packages. As I said, the packages are compiled C code and a couple of Lua functions. So I'm not installing the packages or storing the packages in Ceph at all. The only thing I'm storing is the name of the package you can see it here. Where's the name? Yeah. So I'm installing the name of the package. So this is the add package. There's a Radius object, and I install it as an OMAP attribute for each package. So each package is an OMAP attribute. This is how I do that.
Cool. Yeah, thanks.
Okay. Sure. Martin?
How's it, guys? Thank you, Yuval. I've just got a question regarding the LuaRox and the whole packaging. Or maybe it's more of a suggestion, but wouldn't it make more sense, or would it make sense to package all of the LuaRox outside of the RGW and just upload a big tar file that gets kind of untarred in a certain place, and then you run from there? So let's say, I don't really know. I mean, the times that I've used LuaRox, I've got burnt with it. But you kind of have a main.lua, which would be the code that the RGW, that your C code will call, and all the packages that it needs. I know that, I mean, there's certain link libraries and stuff that you might need and reference. That could be a problem. But yeah, just asking.
Yeah, so I think it should be doable. I mean, even in the current case. So you'll have to install it where we're looking for it. So when you add a package, the only thing it does, it adds us to this Radius object or this OMAP value, and then it is using LuaRox to install it in a certain location. There's nowhere in the code that I'm checking that in your Lua script you imported a package that you added to the list. So in theory, you can do your own packaging, this tar file, go put that in the right place. You have to put it in the right place, like in the where the RGW is looking for it. And then don't add any packages in the command line. Oh, no, you're right. I'm deleting everything there. So to allow for external packages kind of mode, I'll have to change it. I see, yeah. So right, so the install packages script, what it does, the first thing it does, it removes everything. It calls remove all. So for that to actually work, I'll have to have like a flag saying don't do the remove all, and then it's like external packages, it's your business. So if you open a tracker, this is really a very simple fix to do, and then we can have this external mode where we're not using the RGW to install packages or anything, and it's really up to you to do all the work.
Yeah, cool. I'll chat you offline about that. It's just a thought that came to me.
Yeah, I think it makes perfect sense. Yeah, because I agree. Sometimes, I mean, there's a reason why most of the code in this install package function is grabbing the STD error messages coming out of LuaRocks and exposing them to the user. This is because many cases the LuaRocks fails for all kind of reasons. And yeah, you may say, I don't need your favors. I'll package everything, make sure that it works on my system, and you'll just use it. And this is a valid approach here.
Yeah, thanks. I mean, just to add what Martin said, I think that the context is that we have containers that we run a containerized deployment of Quincy, and so obviously in our RDS gateways we need to now package in GCC and make, because every time we restart the gateway, it's a completely new container, and we then need to. So we always have to make sure that we have all the build packages in, which is not ideal. But I mean, we're living with it at the moment because it's. I mean, obviously we want to use the stuff, but I think, Martin, if I'm correct, that's the context in which
it makes sense. Although I've asked the owner of the Ceph container to add all the bits that were missing. So in the next version of something, it should be there already installed. Like make and GCC and LuaRocks, everything should be installed there. So it should be okay. But I agree. I mean, what you suggested, regardless, is a good suggestion, and I should probably do that.
Yeah, great. Thanks.
Sure.
Any other questions? Okay. Well, thank you, Yuval, for providing us content for our Tech Talks. And thank you, everybody, for joining us, both on Jitsi and the live stream as well. And this recording will be put up relatively soon.
Thank you. Thanks, Mike. See you guys.